So here we are on page 6, and we're going to draw the Coulomb curve of water, or the graph of temperature against time in minutes of water. Okay, so you could write your title of your graph in two ways. We could write it graph of temperature against time for water, or the Coulomb curve of water. Now this here is the more popular way to describe this graph. Okay, so we're going to start at water vapor at 150 degrees and go to ice at 10 degrees Celsius. Now because it's water, we have again our important points, our 0 degrees, our 100 degrees Celsius, and this here depends on what the question gives you. So here is 150 degrees and we're going to minus 10 degrees Celsius. Okay, we need our labels: temperature in degrees Celsius, this is a bracket here, and our time in minutes. Okay, so here we're using time in minutes and not seconds, because these changes don't occur in seconds, they take some time. And also heat is being what? Over time heat is being, now this is Coulomb curve, so heat is being removed, okay, not added. So be careful if the question wants you to draw a Coulomb curve or if it wants you to draw a heating curve. So we are starting at, where would we start? We would start here. Okay, we are cooling the gas from 150 degrees. So we will be decreasing the temperature all the way down to 100 degrees. And here at 100 degrees Celsius, we know that there's a phase change. Okay, a change of phase from gas to liquid. And then we would cool again all the way down to 0 degrees Celsius. And then here another phase change will happen. Okay, from liquid to solid. And then we will cool the solid a little more all the way down to minus 10 degrees. Okay, so if we look at the previous graph, it's opposite. Okay, we started here and we went up. And in this one, for the Coulomb curve, we're starting at a high temperature and we're decreasing. So now let's write in our important points. So I'm going to label. I'm going to start here. This is my A, B, C, D, E, and F. Okay, and we're going to be writing what is happening between these stages and at these stages. So here between A and B we have gas only. Okay, so the gas molecules will be spaced out, high kinetic energy. Alright, and here we're seeing a decrease in temperature, so you could write that in. So at A, C, we have gas only. We have a decrease in temperature. Sorry, this is AB. Okay, AB. Decrease in temperature. So high kinetic energy. Heat is removed. Okay. And while the molecules have high vibration, at BC, we have a phase change from gas to liquid. And we call here, what did we see on our simulation? What was here called? Condensation. Okay, condensation was happening here. And here we are taking the gas molecules spread far apart and we're bringing it back a little closer together to form liquid water molecules. And here is gas and liquid at the same time at BC. Now at CD we have liquid only. And our liquid molecules. And here we are decreasing temperature again. For BC, we had no temperature change. This is the most important part of this graph. Okay, no temperature change. So at CD now, we have decreasing temperature and heat being removed. Now pay close attention to what is happening at these phase changes. So the phase change is what we want to focus on. Here, what do you think is happening to the heat that is being removed here? What is happening to this energy? Well, the energy here is being used to form bonds. So at BC, bonds are formed. Okay, so we go in closer from gas to liquid. And DE here is another phase change. So DE is another phase change from liquid to solid. So here we have both liquid and solid states. And we have no temperature change, right? Because bonds are being formed. And we saw in the simulation what the bonds look like, right? They were the black lines between the water molecules. So here's what that looked like. And then at E and F, what we have happening here? We have solid only. Okay? So E and F, we have no phase change, but we have solid only. Now we talk about here being condensation, but at this phase change here, what is that process called? That process is freezing. And freezing occurs at 0 degrees Celsius. The 100 degrees Celsius point and the 0 degrees Celsius point are two values that must be on your graph. If you don't have those two values when you have to draw this type of graph or this sketch, you're going to lose marks. Because we know water boils at 100 degrees Celsius or very close to it. It depends on if your water is pure water or if it have impurities in it. And it freezes at 0 degrees Celsius. So pause and take down your notes. I think you would have enough space at the bottom of the page to write. And then we will merge both graphs, the cooling curve and the heating curve, on page 7 on this graph here. Questions that you will get will most likely look like this graph. So do you notice there is no negative value here? We start directly at 0 degrees Celsius. So the lab that we will be looking at will start at ice at 0 degrees Celsius. So on the same graph below, we're going to show both the heating and cooling curve information from ice at 0 degrees Celsius water to water vapor at 120 degrees Celsius. And water vapor at 120 degrees Celsius to ice at 0 degrees Celsius. So the first things you want to do is label your axes. Temperature in degrees Celsius, time in minutes. We want to put in our important points, our 0 degrees Celsius, our freezing point. We want to put in our 100 degrees Celsius here, and any other values that they give you in the question. So they gave you 120 degrees Celsius, right? And if you use your ruler and you go across, please use a ruler, right? That should be a point there. Your 100 degrees should be that point there, and your 0 degrees here. Okay, so make sure when you're drawing them, they line up to what temperature it's supposed to be. Right, so we could put in what states we have here. At this state here, we have both solid ice and liquid. At this stage here, we have liquid only. Here we have liquid and gas. Here we have gas only. And let's put in the processes that happen at phase change. So here is a phase change. And here's a phase change as well. And let's give the names of the processes. So here we have freezing or melting. Okay, both points are the same, 0 degrees Celsius, right? So freezing and melting happens at 0 degrees Celsius here, and we have a phase change. At 100 degrees Celsius, we have condensation, or we have boiling or evaporation. Okay, and boiling is the more popular one. Now there are some words that we need to know, and one more step to this. At the phase change, there is something called latent heat or latent energy. Okay, so latent heat, and this one here, from where we have solid going to liquid, we call this the latent heat of fusion. And here, our phase change, we call this phase change the latent heat of vaporization. Okay, latent heat of vaporization. Now, for your lab, you would need to identify where your phase change occurs on your graph and label your latent heat of vaporization. So you could either write it on the graph itself, or you could label A, B, C, D and identify in your discussion where your latent heat of vaporization is and where your latent heat of fusion is. So now let's talk about what is this latent heat of fusion and what is this latent heat of vaporization. So one thing to note with all these change of state is that no matter what state or what process is happening here, water remained water. Okay, so during a change of state, the chemical composition of the substance stays the same. Water will still be water at any part of this process. Okay, it will just be either frozen water, liquid water, or gaseous water. Okay, so that's important to note. We wouldn't start with solid ice and end up with liquid gold, right? Water will stay water right through. Okay, so be sure to add this note to your notes as well. Okay, this is very important. So let's take a closer look at what this latent heat of fusion and latent heat of vaporization is. So in areas where phase change occurred, which was the conversion of solid to liquid or liquid to solid or liquid to gas and gas to liquid, we have these flat portions of the graph, and we call those latent heat of fusion, or on the next page we will talk about latent heat of vaporization. So let's first look at the solid and liquid. Let's first look at the solid converting into the liquid and the liquid changing into solid. So the word latent means hidden. And we could see here on the graph, although we are supplying heat, there is no change in temperature. So it's almost as if this heat doesn't exist. We know that we are supplying heat to the system. But as we said before, the heat is being used to break the bonds from a solid to form a liquid. That's why there is no temperature increase. So when we change from a solid to a liquid, or a liquid to a solid, that heat energy is called the latent heat of fusion. And we use a capital L as a symbol for latent heat of fusion. And that latent heat of fusion for a solid is the heat energy required to change it from a solid to a liquid without any temperature change. So the heat absorbed to cause the solid to melt to the liquid is called the latent heat of fusion. So this here is the general definition of what the latent heat of fusion is. Now, each substance has a different value for the energy required to change it from a solid to a liquid. That heat energy is called their specific latent heat of fusion, and we use the letter L, so the common letter L and a subscript of F. So the specific latent heat of fusion for ice, which is solid water, would be different to the specific latent heat of fusion for gold. You would need to supply more heat energy to melt solid gold to liquid gold than you would need to melt ice to liquid water. So this is what the specific latent heat of fusion is. And this definition here is something you would need to learn. The specific latent heat of fusion of a solid substance is the heat energy required to change 1 kilogram of it from solid to liquid without any temperature change. And this topic that you're learning now, if you are doing physics in Form 4, this is one of the founding lessons for thermal energy again. Okay, so thermal energy here that we are doing at this level are just part of the entire topic. Thermal energy is a very big topic. So there will be other lessons if you choose to do physics for Form 4 and Form 5. Okay? Now, there's a formula to find the specific latent heat of fusion. That formula is the heat energy supplied divided by the mass of the substance. And these are the symbols we use. So here we have common L subscript F is equal to E, which represents the heat energy, and this little h subscript h just shows that this energy is due to heat. Later on you will learn about different types of energy. So we use this h here to show that this is energy due to heat. And the M is for mass. So this formula you would need to learn as well. Now the units for the specific latent heat of fusion is joule or joules per kilogram. And those are the units because the unit for energy is joules and we are dividing joules by mass, and the unit for mass is kilogram. So we could write it like this, or we write it joules per kilogram. The specific latent heat of fusion for ice is this value here, 340,000 joules, or if we change it to the scientific form or scientific notation, it's 3.4 by 10 to the power of 5 joules. Or if we convert it to kilojoules by dividing by 1,000, it's 340 kilojoules. Okay, so these are the ways we could express these large values. And converting large numbers to scientific form or scientific notation, okay, or standard form is a lesson that you should have done in Form 1. Okay, now if we rearrange this formula here and we wanted to find the heat energy instead, we would take the heat energy. So this here is heat energy is equal to mass multiplied by, and the L subscript F is the specific latent heat of fusion. Now this value here, you are not required to learn off this value. If you are given a calculation question, they will give you this value. So let's take a look at some examples using these formula. So on page 8 we have some questions here. So let's look at example 1. 1 kilogram of copper and 1 kilogram of nickel. So 1 kilogram here is the mass of these substances, right? The mass are both heated continuously at the same rate. Determine which metal will completely melt first. Use a value of 205 kilojoules per kilogram for the specific latent heat of fusion of copper, and use a value of 297 kilojoules per kilogram for the specific latent heat of fusion of nickel. Okay, now we're talking about latent heat of fusion, so we know that we are moving from solid to liquid. Alright, there is no temperature change at this point. And for copper, the specific latent heat of fusion is 205 kilojoules per kilogram. And for nickel, the specific latent heat of fusion is 297 kilojoules per kilogram. Now the mass is the same, okay? We're using the same amount of copper and the same amount of nickel. Now the mass is the same. 1 kilogram of feathers is equal to 1 kilogram of flour. Okay? 1 kilogram of whatever it is, no matter what it is the same amount. Okay? So just keep that in mind. Now, we want to know which one is going to melt first. Now, how much energy does it take to melt? Now, do you remember what your definition is for specific latent heat of fusion? Let's go back. The specific latent heat of fusion of a solid is the heat energy required to change 1 kilogram of it from solid to liquid without any temperature change. So basically, what this is saying is that this is the amount of heat energy we need to melt 1 kilogram of solid. Okay? So here we are using 205 kilojoules to melt copper. We are using 297 kilojoules to melt nickel. So which one would melt first? The one that uses less heat, right? So when we reach a value of 205 kilojoules, copper will start to melt first. When we reach 297 kilojoules, then nickel will start to melt. So a real-life application of this would be, for example, if we wanted to make a pot and the pot would be exposed to heat energy of, say, 260 kilojoules per kilogram. Which material would we choose to make that pot out of? Now, we wouldn't choose copper because copper would melt before we even reach this 260 kilojoules per kilogram. We would want to make the pot out of nickel because even though we reach this temperature, it wouldn't melt because to melt nickel we need 297 kilojoules. Okay, so this is a real life engineering application of why we learn this topic. So let's look at question 2. 30 grams of molten gold is allowed to solidify. It releases 1890 joules of energy to the surrounding environment as it does so. What is the specific latent heat of fusion for gold? From page 7, we know the formula to find specific latent heat of fusion is the heat energy divided by the mass of whatever solid we're using. And we know we're using latent heat of fusion, so we know we're going from solid to liquid. On page 7, we also said the units is joules per kilogram, okay, which means we're dividing the heat energy by kilogram. Now, this kilogram is important here. It means that we cannot, in our calculation, use grams. We must use kilograms. So we are going to convert this 30 grams into kilograms. 1000 grams is equal to 1 kilogram. 30 grams will be 30 divided by 1000, which is 0.03 kilograms. We move the point 2 places to the left. Now, the latent heat of fusion is equal to the heat energy, and they gave us that heat energy is 1890, and we're going to divide that by the mass, 0.03. You wouldn't need a calculator for these things, okay? The calculations would be simple. Dividing by a decimal, we move the point such that we get a whole number as our divisor, and the number of places we move this point, we do the same thing here. So if I move this point 2 places, it means I am adding 2 zeros here. So I'm really dividing 189,000 divided by 3. And again, you don't need any calculators here. 18 can be divided by 3 6 times. 3 could go into 9 3 times. And the rest are zeros. Okay? and your units is joules per kilogram. And if you wanted to put it in kilojoules, you would divide by 1,000 and you would have 63 kilojoules per kilogram. Number 3. A metal at the temperature at which it melts is heated until all the metal has become liquid. It takes 41 kilojoules to completely melt the metal, and its mass is 0.2 kilograms. What is the specific latent heat of fusion of the metal? So we're talking about fusion again. So we're going from solid to liquid, and we want to find the specific latent heat. So they gave us the heat energy, which was 41 kilojoules, which is 41, and kilo means 1,000, right? Joules. And we have our mass. Our mass they gave us already is in kilograms, so we don't need to change that. Now the formula on page 7 for latent heat of fusion is the heat energy divided by mass. So that is 41,000 divided by the mass they gave us is 0.2. We're going to move this point one place to make the divisor a whole number, which is 2. And then we'll move this point here one place. So it's an extra 0 we're adding there. So let's rewrite that. 41. Now it becomes 410,000 divided by 2. And no calculators again. 2 could go into 4 2 times. 2 cannot go into 1, so we put a 0, but 2 could go into 10, so we put a 5 there, and we have 3 zeros, okay? 0 divided by 2 is 0. So here we have the specific latent heat of fusion of the metal in joules per kilogram. Or if you wanted to put it into kilojoules per kilogram, we divide this by 1,000. And we will get 205 kilojoules per kilogram. Determine how much energy is needed to melt 2 kilograms of ice. And we want to use a value of 334 kilojoules per kilogram for the specific latent heat of fusion of ice. So they gave us LF, which is 334 kilojoules per kilogram. M, they already gave us mass in kilograms already. So on page 7, the formula to find the heat energy was mass multiplied by the specific latent heat of fusion. 334 multiplied by 2. And don't forget this part here. It is kilojoules per kilogram. Okay? And that's it for calculations for specific latent heat of fusion. Now on page 9, we would look at the specific latent heat of vaporization. The formula is the same, but the specific latent heat of, and this here should be vaporization. I would have fixed that in your copy, so your copy should have had vaporization here, right? Is different to the specific latent heat of fusion for ice, right? So it's the same formula, okay, in both cases, except we have to make sure that we are using the correct value here when we are changing 1 kilogram of a liquid to a vapor. And the calculations are the same, okay? So all the calculations that we did on page 8 will be the same way we would do it for the specific latent heat of vaporization. A pan of water reaches 100 degrees Celsius, but the pan is still left on the heat. So eventually all of the water turns into water vapor. So our process here, our change of phase is liquid to gas, okay? So for vaporization, it's a change from liquid to gas. Calculate the energy needed to evaporate 1.2 kilograms of water contained by the pan, and use a value of 2258 kilojoules per Kelvin for the specific latent heat of vaporization. So the same formulas we're going to use. They gave us a mass and they gave us it in kilograms already. Now this is L subscript V for vaporization, okay? 2258 kilojoules per kilogram. And the same formula, we're going to use heat energy is equal to mass by the specific latent heat, and in this case it's vaporization, not fusion. And 1.2 by 2258. When we multiply, so primary level multiplication here by decimals, we multiply, we don't need a calculator, we multiply without the decimal place, okay, and the answer that we get, we put back one decimal place here because of that there, right? So our answer is 2709.66 what kilojoules, okay, and that's our answer here, 2709.6 kilojoules. And it's the same calculations as we would do on page 8. The only difference is we are using the specific latent heat of vaporization, and you would need to know when to use the fusion and when to use latent heat of vaporization. So after you revise this topic, you can feel free to try activity 2. And the next lesson, we would look at a lab, and we would write up a complete lab for the heating curve of water. So pay close attention to the graph on page 7. The graph that you would need to plot for the lab will look similar to that. So as soon as you complete activity 2 and you have a good score in that, we'll move on to the lab. On page 10, there is a little summary chart given the differences between heat, temperature, and thermal energy. So this is just for you to learn and to remember. Again, here, how is it expressed? We would not be using Fahrenheit in any of our calculations or notes, but it's just for you to have a general knowledge that yes, temperature is recorded in Fahrenheit as well. And that brings us to the end of lesson 1, and I'll see you in the video for the lab.